Welcome everyone to the first video lecture for PT 5430, Functional Neurobiomechanical Relationships. In this first lecture, we're going to focus on moving through the foundational knowledge that is needed for the class as a whole. With any luck, most of the material that we encounter is going to be a refresher for you. This part of the course is about making sure that we all have shared language that will aid you in your ability to understand the material that appears later in the class and allows you to talk professionally about patient movement and function. The content of today's lecture is covered in Chapter 1 of the Newman textbook. The foundational knowledge we will cover over the next few weeks relates to our more general goal of understanding human movement. We will draw heavily on three areas of scientific study. We'll draw upon anatomy, which is the science, the shape and structure of the human body and its parts. We'll draw upon biomechanics, which is a discipline that uses the principles of physics to quantitatively study how forces interact with a living body. And we'll draw upon physiology, the biologic study of living organisms. So, what is biomechanics? Here's a definition. Biomechanics is the study of forces that are applied to and exist within the body, and the body's reaction to those forces. This definition can be split into two parts, which are highlighted in red and blue. The first part in blue considers forces. This is the study of kinetics. The second part in red considers how the body moves through space. This is the study of kinematics. As DPT students, one of your main aims is going to be facilitating the recovery of function. In a basic science class like this one, you should be interested in how the foundational knowledge you're encountering relates to function. By function, generally we mean the ability to do things, in particular, those things that are meaningful to us. Let's look at another definition of biomechanics. This definition is the application of mechanical laws to living structures. The notion of mechanical laws is very abstract, similar to a number of the concepts that we'll encounter throughout the class. But mechanical laws have fundamental consequences for understanding function. For example, let's take the most extreme case of functionality. In performing a particular action, am I going to live or am I going to die? What I'm about to say is not a joke, although it's going to sound like one. You have a spider, a dormouse, a human, and an elephant that are about to be pushed off the Empire State Building. Which one would you rather be? Sit back and think about this for a second. The definitive answer to this question comes from biomechanics. Mechanical laws relating concepts such as area, volume, mass, forces due to gravity, and forces due to drag tell us that it's a really, really bad idea to be an elephant. In our scenario, the spider will be unharmed. The dormouse has the potential to escape with only minor injuries. The human, in the unlikely event that they survive, will never be the same again, and the elephant will quite literally go splat. The study of biomechanics has produced a wealth of scientific knowledge that is spread over a number of well-developed subfields. These include areas of tissue biomechanics, developmental biomechanics, industrial biomechanics, sports biomechanics, and medical biomechanics, where the common focus in this area is orthopedic biomechanics. Understanding normal anatomy, normal biomechanics, and normal physiology provides a perspective on understanding impaired function and pathology. A common approach in the study of pathokinesiology, that is the study of abnormal human movement, has been first to ask, what does normal look like? For example, when we look at gait, we will start by considering the characteristics of the gait of a young, healthy adult before we move to considering pathological gait. So let's get started reviewing some of the foundational concepts in biomechanics. Kinematics is the branch of mechanics concerned with the motion of objects. That is, without reference to the forces that cause the motion. The next foundational concept that we need to consider is that of a reference system. You cannot talk sensibly about kinematics or kinetics without having a reference system. The commonly used reference frame identifies three cardinal planes. The word cardinal here means of greatest importance. The particular orientation of these planes is tied to a person standing in the anatomic position, as we see depicted here. These planes are the horizontal plane, the frontal plane, and the sagittal plane. We will start talking about gait patterns later in the semester, and we will spend most of our time focused upon sagittal plane kinematics. This is the particular plane where most of the action is occurring. Here, I'm using the word sagittal when I talk about sagittal plane kinematics to let you know that we are talking about patterns of motion that occur when the body is viewed from the side. The commonly used reference system also specifies three axes of motion. We can use these axes as a reference frame for defining both translations and rotations. For example, we can talk about a movement in the x direction. We can also talk about a rotation about the x-axis. The origin of the x, y, and z axes in this coordinate system is located at the intersection of the axes. There are two basic types of kinematic motion. On the left, we're seeing an object being translated, that is, undergoing a translational motion. On the right, we see a depiction of rotational motion. We will present more formal definitions of the differences between these motion types on the next couple of slides. A translational motion is said to occur if all parts of a rigid body move parallel to and in the same direction as every other part of the body. Translational motions can be rectilinear or curvilinear. The word linear simply means to be arranged in or extending along a line. Rectilinear motion refers to motion along a straight line. Curvilinear motion refers to motion along a curved line. Walking in a straight line provides a nice example of translational motion. In the picture here, we see the person starts on the left and moves across the screen to end up on the right. All parts of their body have been transported, and we therefore have, by definition, a translation. When we look closely at this motion by accurately recording the position of the person's head as it moves through space, we don't see rectilinear motion. Instead, what we see is vertical oscillation as the head raises and lowers slightly by about 5 centimeters. Thus, in this case, we have a curvilinear motion. In rotational motion, a rigid body moves in a circular path around some pivot point. Here we see a gymnast on the high bar. The first thing to notice is that the translational motion of different body parts is very different. The feet are moving through space much quicker than the pelvis, and the hand is almost not moving at all. In contrast to translational motion, we are seeing motion around some point, with different regions of the same body segment not moving through the same distance. We can see rotational motion in elbow flexion extension. This rotational motion here follows the red circle that we've drawn on top of the figure. The center of this circle is the axis of motion. We can characterize the motion of an object based upon its kinematic features. Basic kinematic descriptors include position, displacement, velocity, and acceleration. Position is a location of an object in space, and by space I mean within a particular reference system. On this slide, I'm going to be talking about positions in terms of translations, but I could easily be talking about angular position. So here we have a particular reference system. We can define the axes of this space, x and y. We can define an origin in this space, and we can define the position of a point in this space. Here that point is A. Position is a vector property in that it is characterized by both magnitudes and directions in space. we can define a position with vector coordinates. Here we see the position of point A being defined using coordinates AX and AY. AX gives us the direction and magnitude that we need to move in the x-axis, and AY does the same for the y-axis. So blue line is moving us along the x-axis, and the red line is moving us along the y-axis. Displacement is the change in position. We will often use the delta symbol, shown here, to stand for a change in a particular quantity. So here we see in our reference space a displacement from A to B. Displacement, like position, is a vector quantity, and often we can represent this vector property with the symbol AB with an arrow on top of it. And as before, we can see that we can represent this vector with the two vector coordinates here, delta x and delta y. Remember that the delta symbol here is referring to a difference or a change in a value. So delta x is the difference in the x values of B and A, which is +5. Velocity concerns how quickly a change in position occurs. Here, we're going to be talking about velocity in the x-axis, represented as v, standing for velocity subscript x, can be calculated as the change in position, delta x, divided by the change in time, delta t. Lastly, acceleration. And here again, we're going to be talking about the x-axis. So A standing for acceleration, subscript x, is going to be telling us about how quickly a change in velocity occurs. And so here we have the change in velocity in the x-axis divided by the change in time. Distance and displacement are not the same thing. Distance refers to only the magnitude of a displacement. Here we see two displacement vectors, AB and AC. The displacements between A and B and between A and C are different, since they occur in different directions. So the displacement for AB is +5, the displacement for AC is going to be -5. In contrast, in this example, the distance between A and B and between A and C are the same. Distance is what we refer to as a scalar property. It does not care about the direction of motion. Speed, when we talk about speed, is also a scalar property. It refers to displacement per unit time, regardless of direction, or in other words, it refers to distance per unit time. The next concept that we need in order to effectively talk about movement is the concept of degrees of freedom. The term degrees of freedom is commonly used to refer to the number of independent directions of movement allowed at a joint. Here we see the right glenohumeral joint, or shoulder joint. This is a joint with a particularly large number of degrees of freedom. Motion about this joint can be described using 3 axes of rotation and 3 directions of rotation. Rotations about the mediolateral axis are considered to be either flexions or extensions. Rotations about the anterior-posterior axis are considered to either be abductions, abductions, or adductions, adductions. And rotations about the vertical axis of rotation are considered to be either internal or external rotations. Okay, so let's finally start talking about movements of the human body. Osteokinematics refers to movements of the bones specifically. As we have already said, talking effectively about how the body is moving requires that you use precise language that is shared by the people that you're talking to. In the case of talking about how one limb segment is moving relative to another, it is important to use precise language. Here we have 2 cases of 2 knee flexions. that are superficially similar in how the two segments are moving relative to each other, but they are functionally very different. In the first movement, the proximal segment, the femur, is not moving through space, it is fixed, and the distal segment, the tibia, is moving relative to it. This might be, for example, a person swinging their leg underneath a chair, or backheeling a soccer ball. On the right, the situation is very different. The distal segment is fixed, and the proximal segment is moving relative to it. This might be a person that is initially standing and then moving into a crouch. Here, our language is further defining our reference system. We are taking a perspective using our language that's aiding our understanding. On the left, we will talk about tibial on femoral movement, or distal on proximal movement. On the right, we will talk about femoral on tibial movement, or proximal on distal movement. Arthrokinematics is the branch of kinematics concerned with joint motions. In arthrokinematics, there are three fundamental motions: roll, slide, and spin. In roll, multiple points along the rolling articular surface make contact with multiple points on the articular surface that is being rolled on. In slide, a single point on the articular surface that is sliding makes contact with multiple points on the articular surface that is being slid upon. And lastly, in spin, a single point on one articular surface rotates on a single point on the other articular surface. We can use the tire as an analogy for the three types of motion. In a roll, we have a many-to-many relationship, as different parts of the tire come in contact with different parts of the ground. In a slide or in a skid, one part of the tire comes in contact with many parts of the road. Just as when we're talking about osteokinematics, as we did a few slides ago, in arthrokinematics, we again find it is important to use precise language to understand the motion that's occurring. When we're talking about joint motion, we can use the characteristics of joint surfaces, in particular whether or not an articular surface is convex or concave, to clarify what's going on. Here we see convex on concave rolls, slides, and spins. The convex articular surface is moving relative to the concave surface. Here we see concave on convex motions. Accessory movements refer to the slight passive translations that occur in most joints. A careful look at the arthrokinematics of shoulder abduction shows that the contracting supraspinatus muscle rolls the convex humeral head against the slight concavity of the glenoid fossa. In essence, the roll directs the osteokinematic path of the abducting shaft of the humerus. A rolling convex surface typically involves a concurrent oppositely directed slide. The inferior directed slide of the humeral head offsets most of the potential superior migration of the rolling humeral head. These accessory motions keep the joint in place. Accessory motions are required for effective joint functioning. A classic pathological example of a convex surface rolling without an offsetting slide is shown here. The humeral head translates upward and impinges on the delicate tissues in the subacromial space. Let's look at the arthrokinematics at the knee. We'll start by considering femoral on tibial knee extension. In the diagram here, we're looking at the right leg. The accessory movements of the femur that facilitate the congruency of the knee are anterior roll and posterior slide. As we move towards full extension in this motion, we also see a medial spin of the femur relative to the stationary tibia. This medial spin of the femur is facilitated by the popliteus. Now let's contrastingly look at tibial on femoral knee extension. In this case, we see quite different accessory motions. We see anterior roll and anterior slide. We also see a lateral spin of the tibia relative to the femur in the end range of the movement that's aided by the line of action of the quadriceps. The difference between the two cases that we've got depicted here depends upon whether or not the articular surfaces that are acting in the motion are concave or convex. For a concave on convex surface movement, the convex member rolls and slides in opposite directions. For concave on convex surface movement, the concave member rolls and slides in similar directions. This relationship can be used to help remember the types of accessory motions that you will see, and is referred to as the convex-concave rule. Let's run through the convex-concave rule. For a convex on concave surface movement, the convex member rolls and slides in opposite directions. In other words, if the moving joint surface is convex, sliding is going to be in the opposite direction to the angular movement of the bone. Contrastingly, for concave on convex surface movement, the concave member rolls and slides in similar directions. In other words, if the moving joint surface is concave, sliding is in the same direction as the angular movement of the bone. This rule follows simply from what needs to happen in order to keep articular surfaces aligned relative to one another. For example, let's take the convex on concave surface movement case on the left. Without seeing a slide in the opposite direction, the convex surface will simply roll off of the concave surface. Within most joints, two articular surfaces will fit together best in one particular position. This gives rise to the distinction between close packed positions and loose packed positions. Here we see a table of the contrasting properties of joints in close packed positions versus loose packed positions. In a close packed position, there is maximal joint congruency. That is, the articular surfaces will fit together best in this particular position. In a close packed position, joint ligaments and the joint capsules are going to be most taut, and the joint is going to be at its most stable, with only minimal accessory motions being possible. The major joints tend to be more close packed when the joint is towards the end of its range of motion and when the joint is in extension. A loose packed position is the position acquired during joint immobilizations or joint mobilizations in the clinic. So far today, we've been talking about kinematics, that is, about how the parts of the body that we're discussing are moving through space. Let's now switch gears a little bit and talk about kinetics. When we talk about kinetics, we're concerned with the forces that cause the motions that we're observing. A good place to start with kinetics is to think about the actions of muscles and the forces that those muscular actions produce. We can distinguish muscles based upon the actions that they facilitate. Here we see some different classifications of muscles. Muscles that are agonists act in a way that correspond most directly to the movement that is produced. The biceps is the agonist that moves the elbow into flexion. Muscles that are antagonists act in opposition to agonists. For example, in elbow flexion, the action of the triceps will act in opposition to the action of the biceps. Lastly, muscles that our synergists cooperate to produce a motion. For example, the brachialis and brachioradialis are synergists of the biceps in elbow flexion, and the flexor carpi ulnaris and the flexor carpi radialis are synergists in wrist flexion. Muscles produce torques at a joint. When we're talking about a torque, we're simply talking about a rotational force. Here we see a case where we have an elbow flexion resulting from the contraction of a biceps muscle. We can say that this flexion was caused by the joint torque, the rotational force, that is, at the elbow. A torque is calculated as a force multiplied by a distance. If we want to understand the joint torques that are acting at the elbow joint, we need to know the forces that are acting and how far from the point of rotation these forces are acting. The force here that we've illustrated with the red arrow results from the line of action of the biceps pulling up on the radial tuberosity. As the elbow flexes, you will note that the distance from the point of rotation in the elbow to the line of action of the force vector that we've illustrated as the green line changes. This has important biomechanical consequences. Given our equation here, if we have the same muscle force in both of our joint positions, we will be able to generate a far greater torque when the arm is more flexed and the distance illustrated with the green line is greater. This distance is referred to as the moment arm. So, how do you go about determining the torque that results from the action of a specific muscle? To understand this, let's consider the challenge of how we would determine the joint torques resulting from the action of the posterior deltoid. The common approach has the following steps. First, we need to select one of the cardinal planes of motion in which to define our analysis. So let's identify a plane of motion. Here we're identifying the plane of motion to be the frontal plane. Next, we draw the line of action, and by that I mean the direction that the muscle is pulling in. We can see the line of action depicted with the red arrow. Next, we want to mark the point through which the joint axis passes. This is a point within the humeral head. Lastly, we want to draw the moment arm. This is the green line, the line that is defined by being perpendicular to the line of action and passing through the joint axes. We can go through these same steps to analyze torques acting in the horizontal and sagittal planes. Now that we have a basic understanding of what a torque is and how it's defined, we can consider the difference between internal and external torques. Internal torques are going to be those torques that arise from internal forces. An internal force is produced within the human body, such as the force produced by a muscle. External torques are those torques that arise from external forces. An external force is exerted from outside the body. External forces could include the forces due to gravity or the resistance imposed by a therapist. In the diagram here, we see the internal force that is acting at a distance d from the axis of rotation, and an external force that is acting at a distance d1 from the axis of rotation. The internal torque is equal to the internal force multiplied by the length of the moment arm d. The external torque is equal to the external force multiplied by the length of moment arm d1. Notice that the internal and external torques have opposing directions. The internal torque is acting to pull the forearm in a counterclockwise rotation. The external torque is acting to pull the forearm in a clockwise rotation. If the arm is not in motion, that is, if it's not either flexing or extending, then this means that the internal forces and the external forces must be balanced against one another. We call this particular situation as being in a state of static equilibrium. As we'll see in a few lectures' time, static equilibrium can make it much easier to calculate internal forces in a biomechanical analysis. There are three basic types of muscle action. These are isometric contraction, concentric contraction, and eccentric contraction. Isometric means same length. In an isometric contraction, the muscle remains at the same length during the action, and the internal torque that is produced by the action of the muscle is exactly balanced against the external torque acting on the body. In this situation, the body does not move. Concentric means coming to the center. In a concentric contraction, the muscle shortens as the action unfolds. In a concentric contraction, the torque created by the action of the muscle is greater than the external torque that results from the forces acting on the body. In this case, we see movement in a direction that is opposite to the direction of the external force. Eccentric means away from the center. In an eccentric contraction, the muscle lengthens as the action unfolds. In an eccentric contraction, the torques created by the action of the muscle is less than the external torque. In this case, we see movement in the same direction as the external force. The most frequently encountered external forces are gravitational forces. This means that concentric contractions are frequently anti-gravity movements, where the movement of the body is in a direction opposite to the direction of gravity. Earlier, we defined synergists as muscles that cooperate to produce movement. Muscles acting in what we call a force couple cooperate in a unique way. Even though they're pulling in different directions, as we can see based upon the lines of action in red in the figure, they both act to create internal torques that are in the same direction. Here we see the erector spinae and the sartorius pull on the pelvis in opposite directions. They both work together, each creating a clockwise internal torque. Levers are mechanisms in which two or more forces act on a rigid body about a fulcrum. Fulcrum is just another word for axis. There are three classes of lever defined by the relative locations of the applied force, which we show in red, the resistance or load force, which we show in green, and the fulcrum, which we're showing in grey. We will be thinking about applied efforts in terms of internal muscle forces and resistances and loads as external forces acting on the body. When it comes to appreciating the function of levers, a key concept is going to be mechanical advantage. Knowing the mechanical advantage of a particular lever is going to inform us about how we can move heavy loads with small forces, or how we can move distal segments quickly. In a first-class lever, the applied force, or effort exerted, is on the opposite side of the fulcrum to the load force. To calculate the mechanical advantage for any lever, we divide the length of the external moment arm by the length of the internal moment arm. The external moment arm is the distance of the line drawn between the fulcrum point to the line of action of the external force. As with our earlier calculations, this line is perpendicular to the force vector of the external force. The atlanto-occipital joint is an example of a first-class lever. We see that the center of mass of the head is forward of the fulcrum point in the atlanto-occipital joint. This explains why our head slumps forward when we fall asleep. Counteracting the external force created by gravity's pull on the head is the action of the head extensors, such as the semispinalis capitis. We see that the lengths of the internal and external moment arms are quite similar. We can see in this data box here, there's also appears in the textbook, that the mechanical advantage is calculated to be 1.25. We can also see in this data box how we can estimate the muscle force that must be generated to keep the head upright. In a second-class lever, both the external force and the internal force are on the same side of the fulcrum, and the external force is closer to the fulcrum. A wheelbarrow is a second-class lever. We see the load is placed close to the fulcrum, and the effort is exerted far away from the fulcrum. The actions of a calf raise or standing up on your toes can be interpreted as examples of second-class levers acting in the body. Here, the actions of the gastrocnemius, tibialis posterior, and soleus muscles act to raise up the body. In this example, the external force is the pull of gravity on the center of mass of the body as a whole. We see here that the external force vector falls just behind the axis of rotation located in the first metatarsal head. This creates a short external moment arm. We can see in the data box here that the mechanical advantage is calculated to be 4. A mechanical advantage that is greater than 1 means that a small muscle force can be used to counterbalance a large weight. The pull of gravity on the mass of the body, here 150 pounds in this example, generates a 667 Newton external force. With this mechanical advantage, we can hold up the body using only 167 newtons of muscle force. This is obviously the key functional benefit of this kind of lever. In a third-class lever, the external force and the internal force are again both on the same side of the fulcrum, but now the external force is further from the fulcrum. Holding your arm in 90 degrees elbow flexion is an example of a third-class lever. The internal moment arm is much shorter than the external moment arm. In the data box here, we see the mechanical advantage is calculated to be far below 1. What this means is that a large internal force is required to move a relatively small mass. This functional cost of only being able to move relatively small masses with a third-class lever is offset by the functional benefit of being able to move these masses very quickly and through large ranges of motion. To see an interesting example of the clinical relevance of understanding mechanical advantage, I recommend that you have a quick look at page 24 in your textbook that looks at the application of mechanical advantage to making decisions about tendon transfers. Let's now move on to talking about the related concepts of stress and strain. Strain is simply the measure of how much an object is stretched or deformed. In other words, how much an object has changed its dimensions. Here we see a simple example of a spring that's being compressed via a force imposed from above. This applied force changes the length of the spring. If the spring is originally 10 centimeters long and it's 8 centimeters long after it's been deformed, then the change in length, delta L, is 2 centimeters. Strain is expressed as a relative change in dimension. We calculate strain by measuring how much shorter the object gets under compression and dividing that by the extent of the object before the compression occurred. For our 10 centimeter long spring that was compressed to being 8 centimeters long, we calculate the strain as being 0.8, or alternatively we can say a strain of 80%. Both delta L and L0 in this formula have units of length, and when we divide them through, through by them, they cancel each other out. Because of this, the physical quantity of strain is what we refer to as a dimensionless quantity, and it does not have units. Now let's talk about the physical property of stress. If an object is being squeezed or pulled, here we see a toasted cheese sandwich being pulled apart, the object is stressed by those actions. If the stresses experienced by the material are too great, the material structure of the object, here we're talking the material structure is cheese, will fracture and fail. In more technical terms, when a material is deformed in some way, internal forces are generated in the material to resist that deformation. Mechanical stress is the force per unit area over which a deforming force is applied. The two different cases we see here of a bowling ball acting to compress springs underneath them can be used to illustrate why we need to divide force by area. Imagine in this example that the springs are representing the surface of the material. If all of the force from the weight of the bowling ball is acting in a small area, such as we see on the left, then the stress experienced by the material will be much greater. Alternatively, if the force exerted by the bowling ball is distributed over a much wider area, then the stress experienced will be lower. We divide by area in this formula because we know that the forces encountered by a material will be lessened if they are distributed over a wider area of the material. In the previous slides, I introduced you to stress and strain by looking at compressions, but compression is only one particular type of deformation. So when we look at simple stresses, there's different types of stresses that are useful to get to be able to differentiate. So here we see what we saw in the previous few slides, compressions. So this is what's happening with our springs. When the spring is unloaded, it's longer, and when external forces are applied, it deforms to become shorter and it's compressed. Other simple stresses include tensions, where a material is pulled apart, and shear forces that are acting parallel to the plane. When we're thinking about complex stresses, these are often characterized as bendings, as torsions, and as complex loadings. Many important functional properties of a material are revealed in its stress-strain curve. Here we have the stress-strain curve that we would expect to see for a tendon that has been stretched to the point of breaking apart, to its point of mechanical failure. Data like this is typically obtained in experiments in which a sample of tissue, here we see a sample of Achilles tendon, being gripped at either end and being progressively distended. Each time the two ends of the tissue are pulled slightly further apart, we measure the force that is acting to resist that distension. To calculate stress, we then divide the measured force by the cross-sectional area of the sample. So in our stress-strain curve, we have strain on the x-axis and stress on the y-axis. In our example here, stress denotes the internal resistance generated as the Achilles tendon resists being deformed. And we take that measure of force and we divide it by the cross-sectional area of the sample. Strain is the percent increase in a tissue's stretch length relative to its original pre-experimental length. To understand the stress-strain curve, start by looking at the bottom left of the curve. This is the nonlinear or toe region of the graph. This region reflects the fact that collagen fibers within the tissues are initially wavy or crimped, and they must be drawn taut before significant tension is measured. So we see that we can strain the tissue, we can make it longer relative to how long it was originally, and we don't see any increase in stress. Further elongation beyond this region begins to show a linear relationship between stress and strain. The ratio of stress to applied strain in this region is referred to as stiffness, and also gets referred to as Young's modulus. So here what we see is that in order to calculate a stiffness of a tissue, we look within its elastic region of behavior, and we look to see the ratio between how much change in Y we get relative to X. So when we get a certain change in stress and we divide it by the change in strain that we get, that gives us a value that we call stiffness, and that we also refer to as Young's modulus. The clinical term tightness usually implies a pathologic condition of abnormally high stiffness. A tissue that's elongated beyond its physiologic range eventually reaches a yield point. The physical behavior of an overstretched tissue is referred to as plasticity. The overstrained tissue has experienced plastic deformation. So we see we have two main regions going on in this graph. We have an elastic region and a plastic region. The elastic region has particular characteristic behaviors to it. The key characteristic behavior is that if we stretch a tissue in this region and then let it go, it will return to its original length. If we try to do the same in its plastic region, we will not see the same happen. So at any point when we're in the plastic region, what we're seeing is microscopic failures starting to occur, and that when you stretch a tissue, when you deform a tissue in the plastic region, we end up with the tissue remaining permanently deformed. So once we move past the yield point at the end of the elastic region, the behavior of the tissue is going to change, and that when we strain it further, when we pull it apart further, when we let it go, it's not going to go back to its original shape. Lastly, in this stress strain curve, we reach the ultimate failure point. This is the point when the tissue partially or completely separates and loses its ability to hold any tension whatsoever. The term stiffness has a specific meaning. Stiffness is how a component resists elastic deformation when a load is applied. Elastic deformation is underlined in our definition because stiffness is a property of a material in its elastic region. So here we see our stress strain curve from the previous slide. In the dark blue area, we have its elastic region. We calculate stiffness in this region. So stiffness relates to how a material deforms under load while still returning to its original shape once that load is removed. Stiffness is not the same as the strength of a material. In other words, a stiff material is not technically the same as a strong material. Strength, alternatively, is a measure of the stress that can be applied to a material before it permanently deforms. Here we're talking about its yield strength, or to the point when it breaks. Here we're talking about tensile strength. The units of stiffness are the same as the units of pressure. The SI units are newtons per square meter. The imperial equivalent is pascals. We can understand why stiffness has these units by looking at how it's calculated. Since stiffness is the ratio of stress, which has units of pressure, to strain, which is dimensionless, we will end up with units of pressure. To get a better feel, an intuitive feel for stiffness, and what specific values of stiffness mean, here we can see some stiffnesses that have been calculated for various materials. The units of stiffness that we're looking at here are in gigapascals. So the size of these values would change depending upon what units that you're looking at. Starting with the very stiff materials, we see that stainless steel has a stiffness of 200 gigapascals. Titanium has half that stiffness with 100 gigapascals. Cortical bone has somewhere between 7 and 21 gigapascals of stiffness, depending upon the sample that you're using to measure. Bone cement has a stiffness of 2.5 to 3.5. Tendon has a stiffness of 0.66. And to follow on from our comedy example in the previous slide, cheddar cheese has the remarkably low elastic modulus or stiffness of 0.00037. To make an everyday clinical connection when we're talking about stiffness, here we see some of the mechanical properties of different colors of TheraBand that you might end up using in the clinic. In the first column, we see the resistance created by each TheraBand when we stretch it to twice its resting length. Notice that the changes in resistance are much greater than the changes in stiffness. The difference is accounted for by the change in cross-sectional area. So when we look at the thickness column, thickness obviously relating to increasing its cross-sectional area, we see that both the thickness and the stiffness are coming together to determine the resistance of that particular TheraBand. The next mechanical property that we're going to consider is stress relaxation. Stress relaxation is a dynamical property. By dynamical, I simply mean that it's a property that changes over time. Stress relaxation captures the observation that if you stretch a material and hold it in a fixed stretched position, that you will see a decrease in its resting force over time. Here we see a graphic representing stress relaxation in a tissue. In the blue line of the graph, we see the resistive force that results when we initially stretch the tissue. So up at the top of the screen, we can see this stretching being depicted with the blue arrow. So in this first phase, what we're doing is we're loading the tissue. We're stretching it. Once the tissue is stretched, once we've got it up to point B on the graph, we then fix it in position. We hold the tissue in position. Lastly, over time, what we see is that the tissue begins to adapt to the imposed stress, and the resistance force in the tissue starts reducing. So we can see this then after we're holding it in position, the graph starts to dip down. We're just holding the tissue in position, but the forces that are acting in between the two green bars here and here are decreasing over time. This decrease in resistance force in the tissue is what we mean by stress relaxation. In the context of working with tissue therapeutically, after allowing the tissue to relax, then the tissue could be stretched further. Examples of the clinical application of the stress relaxation principle can be seen in the use of serial casting, Ilizarov frames, and in the use of the Milwaukee brace for scoliosis. Serial casting is a process in which a series of casts are successively used to stretch soft tissues for an extended length of time, and Ilizarov external fixators are ring-like braces. The frame is applied to the outside of the limb and connected through the unbroken part of the bone inside the limb. Now let's consider the concept of creep. Whereas stress relaxation concerns decreased stress in a material that is resisting a fixed deformation, creep concerns slow deformation of a material over time as a result of a fixed load. So, in the case of stress relaxation, we're talking about stretching a material and holding it in that stretch position and seeing how a decrease in the amount of force resisting that stretch is going to occur. In the case of creep, we're talking about applying a fixed force and then looking at the slow change in deformation of the material over time as a function of that applied load. So here we see a graphic representing creep in a tissue. A fixed load or stretching force, so here we see the 30-pound weight, is applied to the tissue. When we do this, we see an initial deformation. So we apply the weight, and then we see the tissue deform. We see it stretch as a result of the 30-pound weight being applied. This deformation is being seen as the blue line in the graph. If we keep waiting, what we see is that the tissue keeps adapting with longer lengths over time. So we apply the weight, we see it deform, but if we wait around for an extended period of time, we will see that deformation keeps creeping up. Examples of the clinical application of the principle of creep include spring wire and rubber band braces. Here we see some knuckle benders, and here we see skeletal traction using weights. Okay, let's move on to the concept of fatigue. Fatigue refers to a process in which a material can become weakened from experiencing multiple repetitive loading cycles. The process can lead to mechanical failures at magnitudes of stress below the ultimate strength of the material. So if a material has become fatigued, it will fail earlier than a material that has not become fatigued. We see fatigue both in non-biologic and biologic tissues. Examples of fatigue in biological tissues include stress fractures, bursitis, that occurs when bursae become inflamed, tendonitis, and most overuse injuries. The next concept that we'll talk about is viscosity. The mechanical property of viscosity underlies some important characteristics of biological tissue that we will discuss in the next lecture. Viscosity is most easily understandable in terms of the motion of a fluid. When motion occurs in a fluid, interactions between the molecules in the fluid produce forces that act to resist motion in the fluid. The key characteristic of viscosity is that the resistance encountered depends upon the velocity of deformation. In the picture here, we see a person moving their hand through water. If they do this slowly, they will experience minimal resistance. If they do it quickly, the resistance force increases dramatically. An everyday example of viscosity can be seen in a door damper. You've all seen these devices at the top of doors. They make it impossible to slam a door. The faster you move the door, the greater the velocity that you're moving the door, the more resistance that these devices create. The final property that we're going to discuss today is viscoelasticity. If someone says that a material is viscoelastic, it means that the material has both viscous properties and elastic properties. Most biological tissues are best characterized as being viscoelastic. They are elastic in that the resistance force in the tissue will increase linearly with how much it is stretched, and it is also viscous in that the tissues will resist with higher forces if that force is applied quickly. Viscosity is a property that's often mistakenly overlooked in thinking about the function of tissues. For example, in the literature, you'll see many examples where tissues are only tested at one speed. This hides the viscous forces that are generated when a tissue is stretched either slowly or quickly. And when we begin to look at more closely at some of the properties of tissues, we'll see these particular forces in action. Okay, that completes our first lecture on the basics of biomechanics. Your goal when you're reviewing this material is to make sure that you know the meaning of all of the concepts covered today. These concepts will turn up a number of times throughout the next few lectures. Okay, thank you.